for a classical computer, right? So, but now, but the idea is that for classical computers, the difficulty of simulating chemicals grows exponentially in the number of atoms. Whereas for quantum computer, the difficulty grows linearly in the number of atoms. So suppose you have a biological protein receptor and you want to know the binding energy of a drug to that receptor. So now we're talking about a lot more atoms. And so should you use a quantum or a classical computer for that? And the idea is that eventually quantum computers will catch up. And whenever they finally do catch up, and they will eventually blow them away. And so that's the idea of the power of quantum computing. So many people think 2018 may be the year of quantum supremacy. This is whenever IBM or Google will announce that their quantum computer outperformed the best supercomputer at some computation. So it'll be some kind of academic, contrived problem, just meant to demonstrate supremacy. But nevertheless, it'll be a huge milestone when it happens. So this could be, a very exciting year for quantum computing. With that said, there are some caveats that even if we do demonstrate quantum supremacy for this contrived problem, real applications for, say, financial modeling or machine learning or pharmaceutical design, they may still be a year or two off, because we have what's different about these quantum computers is that they have noise, which means, so suppose that you typed into your laptop computer, what is 6 times 7, and then sometimes it returned 41, sometimes it returned 46, but a lot of times it returned 42. So that's kind of a new paradigm that people aren't used to, which is that a lot of times it gets it right, sometimes it's wrong, but there's noise. And so for the next year or so, year or two, these companies have been working really hard on taming their noise and trying to reduce this noise. And my job at the lab is to try to find algorithms that are tolerant to noise, find ways to beat the noise, and also to just come up with algorithms for new applications that people might not have thought of for quantum computing. So that's what I do at the lab. So finally, I'll just mention a couple more applications. So a lot of people think that simulating, as Stefan mentioned, simulating physics will be the first kind of application of quantum computers. So actually simulating crystals or superconductors, or simulating chemistry, or simulating the nucleus of the atom. So actually simulating physics, doing science, is probably the first application of quantum computers. But nevertheless, people are also really excited about sort of the next wave of applications which may come afterwards, which would be, say, machine learning. So doing machine learning faster. So you probably have heard that machine learning has applications in self-driving cars, speech recognition, financial modeling. So this next wave of applications is probably where a lot of the money is. Maybe that's a year off. Who knows? We'll see. But anyway, that's the end of my talk, and I'll leave it open for questions and discussion.
A year off. That's nice.
Yeah.
Well, that was really good. That helped a lot. A lot of questions.
I wonder if you'd talk a little bit more about the error problem. When DVDs came in, they had very sophisticated ways of taking out errors. Can you use the same process with qubits?
How do DVDs do it, actually?
It's an error correction code, right?
Oh, error correction code. Oh, right, I see, yeah. Oh, well then yes, and the answer is yes. Okay, right. So that's actually, so classical error correction, which, okay, now that I understand what you're saying, has a direct analog on quantum computers. So for the general audience, let me say that, like, classical error correction, what they do is, suppose they do something called the repetition code, where Now, remember the light switch example. You could store either 0 or 1 with the light switches on or off. Now, suppose you have 3 light switches. 3 light switches, and then you say a 0 or 1 corresponds to all the 3, a 0 corresponds to all the light switches off, and a 1 corresponds to all the light switches on. So what happens if one of the light switches goes bad? Then that means that you can still use majority rule. So you can still say that, well, at least the other 2 are good, right? So if one of them goes bad,
Are good, or only one of them is good?
if only one of them is good, then you're screwed. So I mean, like you need more. You can correct more errors if you just by having more light switches, right? So, but yeah, but this is like it's just a simple example. So 3 light switches can be used to correct an error on a single light switch. If one of your light switches goes bad, you can still recover the information about whether the light switches were on, about 0 or 1. So the same principle is used in quantum computers.
It can be the same principle?
Yeah. So they do. So you just need more qubits, right? More quantum light switches. So you use this repetition code. So the more qubits you have, the more errors you can correct.
Do you think you can make it completely error-free?
No, it's never going to be error-free.
Well, then how can you trust the calculations?
Well, the idea is that with high probability you'll get the right result, right? It's always like some, but even in normal quantum computers, or normal computers, there's thermal noise, right? So there's always some.
It's either 0 or 1. If it's not 1, it has to be 0. But you have 4 states now, so.
No, we still.
0 or 1 is random.
Yeah, we still have just two states. It's still a light, it's a weird light switch. Yeah, so it's still just like a 2-state system in a sense, just kind of with weird properties. Yeah. Go ahead. Good question. Yeah.
I don't know if you remember, but the lab had the 30th anniversary, and Harold Agnew invited 6 of the laureates who'd been here during the war. And Dick Kleinman gave a lecture. He had each one of them work here. And he gave his on quantum computing. Do you know if there was any video taken of that lecture he gave in 1973?
That would be a question for the lab historian.
Yeah,
Whether there's video. I don't actually.
So Don, he said it's probably a question for the lab historian. I will talk with the lab historian and archivist, Ellen Carr, and I will find out, because they do have some film. That would be fascinating to bring out. You guys would love to see it, I'm sure.
Yeah, absolutely, actually. Yeah. 73. Very good.
So they're getting so small and delicate. How sensitive are they to external threats like cosmic rays, for example?
Yeah, that's what I mean.
Yeah, I mean, well, some people are doing some people are putting quantum devices on satellites, not necessarily for computing, but for quantum communication, and then you really have to worry about the cosmic stuff there. But then I think it's really the main, quantum stuff is just so fragile that I don't think it's the cosmic rays that are really the thing to worry about, but just generally any communication to the outside world. If you try to put these things in vacuum, but there happens to be some air molecules around, or just if there's some other defects in your fabrication. So it's really kind of the local stuff that really is the biggest thing. So the local environment, the local defects. Certainly quantum systems are much more fragile than qubits are much more fragile than classical bits. Yeah.
Although with error correction, you can, that should take you quite a ways to do good error correction. It's actually an interesting question in the sense that